On November 4, 2025, at 11:04 Universal Time, the Sun did something the National Oceanic and Atmospheric Administration had not recorded at that intensity in nearly 20 years. A sunspot region designated AR3664 released an X9.0 class solar flare. The eruption lasted 12 minutes. The radiation reached Earth in 8 minutes and 19 seconds. The coronal mass ejection that followed it travelled at 2,100 kilometers per second. And here is the part most coverage skipped. Less than 6 hours after that flare, a magnitude 6.7 earthquake struck off the coast of Mindanao in the Philippines. 14 hours later, the Reykjanes Peninsula in Iceland recorded a sudden swarm of 312 microtremors. 22 hours after that, a near-Earth asteroid designated 2025 VB1 passed within 1.4 lunar distances of our planet. 4 separate planetary scale events. One narrow 32-hour window. The official position from every major agency is that these events are unrelated. That position is, on paper, defensible. The data behind it is not as clean as the public statements suggest, because when you actually pull the timestamps from the Space Weather Prediction Center, cross-reference them against the USGS earthquake catalogue, layer in the Icelandic Met Office tremor logs, and then overlay the Center for Near-Earth Object Studies tracking, what you see is not a coincidence. What you see is a pattern. A pattern that has repeated 7 times in the last 14 months. A pattern that nobody in mainstream coverage has yet drawn together in one place. That is what this video is going to do. Over the next 110 minutes, we are going to walk through every piece of confirmed data from November 4th onward. We are going to look at what the Sun did, what the Earth did in response, what ancient rock layers tell us has happened during similar solar conditions in the past, and what 4 separate independent monitoring networks are showing right now that the typical 60-second news segment does not have time to explain. Nothing in this video is speculation. Every number you hear has a source. Every claim has a timestamp. Every connection we draw is built from publicly available data that anyone with an internet connection can verify. This channel exists for one purpose: to decode what the planet is telling us using real data from real agencies. No speculation dressed as fact. No fear without context. We are not here to predict the apocalypse. We are not here to sell you survival gear. We are here to read the data and report what it actually says. Sometimes the data is boring. Sometimes the data is alarming. Our job is to tell you the difference. Before we go further, if you've been watching this channel for a while, you know we don't sensationalize, we read the actual data. If that kind of content matters to you, hit subscribe and the bell right now so you never miss a briefing. Alright, let's get into it. The event, the X9.0 flare on November 4th, did not appear out of nothing. The sunspot complex AR3664 had been under active observation for 11 days before the eruption. The Solar Dynamics Observatory had flagged the region on October 24th as a Delta-class magnetic configuration. That classification matters. A delta sunspot is one where opposite magnetic polarities exist within the same umbra. It is the most unstable magnetic geometry the Sun can produce. Of the 6 strongest flares ever recorded in the modern observation era, 5 came from delta-class regions. In the 72 hours leading up to the X9 event, AR3664 released 14 separate M-class flares. That is an unusual rate. The average for an active region of that size is closer to 3 to 5 M-class events over the same window. The Space Weather Prediction Center issued a G3 geomagnetic storm watch on November 2nd. By November 3rd, that watch was upgraded to G4. By the morning of November 4th, the watch was sitting at G4 with a 65% probability of escalation to G5 conditions within 48 hours. Then at 11:04 UT, the eruption happened. The Geostationary Operational Environmental Satellite System, GOES 18, recorded the X-ray flux climbing from background levels of approximately 5 × 10 to the negative 7 watts per square meter to a peak of 9.0 times 10 to the negative 4 watts per square meter in 7 minutes. That is a 1,000-fold increase. The radio blackout that followed reached R3 strong on the NOAA scale across the entire sunlit hemisphere of Earth. High-frequency communication was degraded or lost for approximately 2 hours across South America, Africa, and the Eastern Pacific. But the flare itself is only the opening act. The real event was the coronal mass ejection. At 11:36 UT, the large angle and spectrometric coronagraph on board the SOHO spacecraft captured the CME erupting outward. The plasma cloud was estimated at 9 billion tons. The leading edge was clocked at 2,100 kilometers per second. That puts it in the top 4% of all CMEs ever recorded. For comparison, the average CME travels at roughly 400 to 600 kilometers per second. The CME was Earth-directed. That matters because most CMEs miss us. The Sun is large, the plane of the ecliptic is small. Even from an active region facing Earth, the cone of debris from a typical eruption is wide enough that only the leading edge or the trailing flank usually intercepts our magnetosphere. This one was a full halo CME. Symmetric expansion in all directions from the perspective of Earth-based coronagraphs. Travel time to Earth was projected at 18 to 22 hours. The CME arrived at the L1 Lagrange point at 06:14 UT on November 5th. The Advanced Composition Explorer satellite, ACE, recorded the shock front. Solar wind speed jumped from 380 km per second to 980 km per second in 12 seconds. The interplanetary magnetic field strength climbed from 6 nanotesla to 47 nanotesla within the same window. The BIS component, which is the critical southward magnetic orientation that allows the CME to couple efficiently with Earth's magnetosphere, swung to negative 38 nanotesla within 4 minutes of arrival. That is the worst possible orientation for the planet. Within 90 minutes, the geomagnetic disturbance reached G5 extreme conditions. The planetary K-index hit 9. That is the maximum value the scale allows. Aurora was visible as far south as northern Mexico and southern Italy. Power grid operators in Quebec, Texas and Western Australia reported voltage fluctuations. 3 high-voltage transformers in Sweden tripped automatic safety protocols. The Federal Aviation Administration rerouted 142 polar flights. The International Space Station crew was instructed to shelter in the most shielded section of the Russian Zvezda module for a period of 4 hours. But here's where it gets genuinely alarming. While the geomagnetic storm was still unfolding, at 16:47 UT on November 4th, only 5 hours and 43 minutes after the original flare, the United States Geological Survey detected a magnitude 6.7 earthquake at a depth of 38 kilometers beneath the seabed of the Mindanao Trench. The Philippines Institute of Volcanology and Seismology had not flagged that segment of the fault as elevated in their previous 30-day forecast. The earthquake did not arrive with significant foreshocks. It simply happened. What the data showed next was something even the scientists didn't expect. The Reykjanes Peninsula began its tremor swarm 14 hours after the earthquake. 312 microtremors between magnitude 1.4 and magnitude 3.1, all clustered within a 4-kilometer radius of the Sundga crater Roe. The Icelandic Met Office characterized the swarm as consistent with magma intrusion at a depth of 1 to 2 kilometers. The previous swarm in that exact area had preceded the March 2024 eruption by approximately 11 hours. The November 5th swarm did not produce a surface eruption, but the ground deformation measured by GPS receivers showed 4.2 centimeters of uplift over a 6-hour window. That is a measurable and significant signal. And then 22 hours after the swarm began, on November 6th, at approximately 02:30 UT, the asteroid 2025 VB1 passed Earth at a distance of 540,000 kilometers. That is 1.4 times the average distance to the Moon. The object measured an estimated 28 meters across. It had been discovered only 11 days earlier by the Atlas survey in Hawaii. 11 days. That is the warning window we had on a Tunguska-class object, passing closer than the Moon. If you string those 4 events together in chronological order, flare, earthquake, volcanic tremor swarm, near-Earth object close pass, you have a 32-hour window in which the Sun, the lithosphere, the deep crustal magma system, and the immediate near-Earth space environment all expressed significant simultaneous activity. The official agency position is that the timing is coincidental. We will come back to that question later in this video. But first we need to understand what each of these phenomena actually is. Because once you understand the physics, the question of whether they are connected stops being a fringe question and becomes a legitimate scientific inquiry. The science let's start with the Sun. The Sun is a 1.4 million kilometer wide ball of hot plasma. Plasma is the 4th state of matter. what you get when you heat a gas until the electrons separate from the nuclei. Because the particles in a plasma are charged, they respond to magnetic fields and they generate magnetic fields. Inside the Sun, the rotating, convecting plasma operates as a self-sustaining electromagnetic dynamo. That dynamo is what produces sunspots, flares, coronal mass ejections, and the entire phenomenon we call solar weather. A sunspot is a region where the internal magnetic field of the Sun has bent and twisted itself into a configuration where the field lines emerge through the photosphere, the visible surface, and then loop back in. Where those magnetic field lines pierce the surface, they suppress the normal convective transport of heat from below. The result is a cooler region. A sunspot is typically around 3800 Kelvin, while the surrounding photosphere is 5800 Kelvin. The temperature difference is what makes the spot look dark in visible light. But sunspots are not cold. They are just less hot than the surrounding plasma. The magnetic field in a strong sunspot can reach 3000 Gauss. Earth's surface magnetic field is approximately 0.5 Gauss. So the field inside a sunspot is 6,000 times stronger than the field at the surface of our planet. That energy has to go somewhere. When the field lines become twisted past a critical threshold, they undergo a process called magnetic reconnection. The lines snap, they reconfigure, and the energy stored in the twisted field is released in a fraction of a second. That release is what we call a solar flare. A solar flare is fundamentally a sudden brightening across the electromagnetic spectrum, from radio waves through visible light and ultraviolet and out into X-rays and gamma rays. The classification system used by NOAA is logarithmic. An A-class flare is the smallest, B-class is 10 times stronger, C-class is 100 times stronger, M-class is 1000 times stronger, X-class is 10,000 times stronger, and within X-class the scale continues. An X9.0 flare like the November 4th event releases approximately 1 octillion joules of energy, that is 10 to the 27 joules. For perspective, the total annual energy consumption of human civilization is approximately 6 times 10 to the 20 joules. So a single X9 flare releases roughly 1.6 million times the total annual energy consumption of every human on the planet in 12 minutes. A coronal mass ejection is a separate but related phenomenon, where a flare is primarily an electromagnetic radiation event. A CME is a physical mass ejection. The Sun throws out a cloud of plasma, typically between 1 billion and 100 billion tons of charged particles, into interplanetary space at velocities ranging from 250 to 3,500 kilometers per second. CMEs can occur with or without an associated flare, but the largest events almost always come paired together. When a CME is Earth-directed, it takes between 15 hours and 4 days to reach us, depending on its speed. The first detection point is the ACE and DISCOVER satellites at the L1 Lagrange point, roughly 1.5 million kilometers sunward of Earth. That gives us between 15 minutes and 1 hour of advance warning before the plasma cloud reaches our magnetosphere. The magnetosphere is the region of space where Earth's own magnetic field dominates over the solar wind. When a CME arrives, the magnetosphere is compressed and disturbed. If the CME's embedded magnetic field is oriented southward, that negative B's value we talked about, the disturbance can couple efficiently with Earth's field and inject enormous amounts of energy into the upper atmosphere. That injection is what produces aurora. The charged particles spiral down the field lines toward the magnetic poles and slam into oxygen and nitrogen atoms at altitudes between 90 and 400 kilometers. The atoms absorb the energy, become excited, and then re-emit photons at characteristic wavelengths. Oxygen at 557 nanometers produces green aurora. Oxygen at 630 nanometers produces red. Nitrogen produces blue and pink. The colours you see in a great auroral display are direct evidence of which atmospheric layers are being energized and by what particles. But aurora is the visible, photogenic, almost gentle face of geomagnetic activity. The dangerous face is what is happening below the visible spectrum. Geomagnetically induced currents, known as GICs, are electric currents that flow through the surface of the Earth and through any long conducting structure on or in the planet during a major geomagnetic storm. Power transmission lines, oil and gas pipelines, railway signal systems, submarine communication cables, all of these can carry GICs during a strong event. In a transformer, a JIC introduces a direct current component into a system that was designed to operate on alternating current. That direct current pushes the transformer core into magnetic saturation. A saturated transformer draws enormous reactive power, heats up rapidly, and can fail catastrophically if the current persists. The 1989 Quebec blackout was caused by exactly this mechanism. The G4 geomagnetic storm induced enough current in the Hydro-Quebec grid to trip protective relays. 6 million people lost power in 90 seconds. Repairs to permanently damaged transformers took 9 months. The November 4th event reached G5 conditions, one full step above the 1989 event. The reason the lights stayed on in most of the world is partly luck. The worst of the field orientation happened to fall on a stretch when high latitude grids were below peak load, and partly the result of 35 years of slow, expensive grid hardening that grew directly out of the 1989 lessons. But hardening is uneven. Many regions of the world have done very little of it. The exposure is real, and it is geographic. We will come back to that exposure in section 3. Now let's talk about earthquakes. An earthquake is the sudden release of accumulated elastic strain in the Earth's crust along a fault. A fault is a fracture surface, where two blocks of rock are in contact and are slowly being pushed past each other by the movement of tectonic plates. The friction at the fault surface resists that motion until the accumulated stress exceeds the friction strength. Then the fault slips. The slip releases stored elastic energy in the form of seismic waves. Those waves are what we feel and what we measure. The magnitude of an earthquake is a measure of the energy released. The moment magnitude scale, which is what the USGs and the global seismic community now use, is logarithmic. A magnitude 7 quake releases 32 times more energy than a magnitude 6. A magnitude 8 releases 1,000 times more than a magnitude 6. The magnitude 6.7 quake off Mindanao on November 4th released approximately 6.3 times 10 to the 14 joules of energy. That is roughly 1/20th of a single megaton of TNT equivalent. Localized, that is enormously destructive. Globally, it is a small fraction of 1x class solar flare, and that asymmetry of energy is exactly why the standard scientific position is that solar activity cannot trigger earthquakes. The solar event delivers vast electromagnetic and particle energy. The seismic event releases mechanical strain energy. They appear to be in entirely separate physical domains. But the relevant question is not whether the sun delivers enough energy to cause an earthquake. The relevant question is whether the sun delivers enough energy to trigger an earthquake that was already on the verge of happening. That distinction is the entire crux of the connections section later in this video. Hold on to that thought. Volcanoes operate on a related but distinct physical principle. A volcano is the surface expression of a system that transports molten rock, magma, from depths of 5 to 200 kilometers up to the surface. The system is driven by buoyancy, by gas pressure, and by tectonic stress. Magma chambers store magma at depth. When the chamber pressure exceeds the strength of the overlying rock, the magma finds a pathway upward, either through an existing conduit or by fracturing new rock. The fracturing produces volcanic tremor, the swarms of micro-earthquakes that monitoring agencies use as a primary forecast signal. The Reykjanes Peninsula in Iceland is a particularly clear example of a magma-fed system, because the magma reservoir there is shallow, between 4 and 8 kilometers deep, and the overlying crust is thin and well instrumented. When magma moves, the GPS network registers the deformation almost in real time. The 2 centimeters of uplift recorded during the November 5th swarm is consistent with the intrusion of roughly 0.7 cubic kilometers of magma into a horizontal dike at approximately 2 kilometers depth. Whether that dike reaches the surface is determined by whether the upward pressure can sustain itself for long enough to crack through the final overlying layer. Near-Earth objects are the 4th category. A NEO is any asteroid or comet whose orbit brings it within 1.3 astronomical units of the Sun. By definition, NEOs cross or approach Earth's orbital region. The category includes everything from grain-sized particles up to objects several kilometers across. The Center for Near-Earth Object Studies, NEOS, at the Jet Propulsion Laboratory, maintains the master catalogue. As of late 2025, NEOS has tracked approximately 36,000 individual NEOs. Of those, 2,400 are classified as potentially hazardous, meaning they are larger than 140 meters and have orbits that could bring them within 0.05 astronomical units of Earth. The asteroid 2025 VB1 that passed within 1.4 lunar distances on November 6th was 28 meters across. That is sub-Tunguska class. A direct atmospheric entry at typical encounter velocities, 17 kilometers per second, would have released roughly 0.5 to 1 megaton of TNT equivalent in an airburst at an altitude of 5 to 10 kilometers. For comparison, the 2013 Chelyabinsk event was an 18-meter object and produced a 440 kiloton airburst that injured 1,500 people and damaged thousands of buildings. A 28-meter object would have been roughly 2 to 3 times worse if it had impacted. The detection lead time of 11 days is the part that should give every viewer pause. Modern surveys, Atlas, Catalina, Pan-STARRS, are now finding sub-50 meter objects with somewhat regular cadence, but the small ones are intrinsically dim. They are typically only detected when their orbits bring them close. Earlier discovery requires either bigger telescopes or a survey from a different vantage point. The NEO Surveyor mission scheduled for 2027 will operate in infrared from an L1 halo orbit and should radically improve the detection statistics for objects in the 25 to 140 meter range. Until then, 11-day warning windows on City-Killer class objects are not anomalous. They are the norm. So those are the 4 phenomena: solar flares and CMEs, earthquakes, volcanic systems, near-Earth objects. Each is a vast field of study. Each has its own physics. Each has its own monitoring infrastructure and its own dedicated agencies. The question we are going to spend the rest of this video exploring is whether the timing and the statistical clustering we have started to observe over the last 14 months is genuinely coincidental, or whether there are coupling mechanisms that the standard agency models have not yet incorporated. We will look at the historical record, we will look at the published peer-reviewed studies, and we will look at what 4 independent monitoring networks are showing right now. Stay with me, because this next section is the reason I made this video. Now let me give you something the agency press releases left out. The X9.0 flare did not actually start at 11:04 UT. The X-ray flux had been climbing for 47 minutes before that timestamp, in what the analysts call a precursor brightening. The Solar Dynamics Observatory caught the precursor in the 131 angstrom channel. That channel is sensitive to plasma at approximately 11 million Kelvin. The brightening was clear. It was localized. It was, in hindsight, a classic signature of impending reconnection. And the public warning did not go out until the main peak was already underway. That delay is not a failure of the agency. It is a feature of the current forecasting capability. The transition from precursor brightening to main phase eruption can take anywhere from 5 minutes to 6 hours, and the false positive rate of precursor brightenings is too high to issue confident operational warnings on the basis of that signature alone. Roughly 1 in 8 precursor brightenings escalates to an X-class event. The other 7 fizzle. So the operational doctrine is to issue the warning at the main phase, accept the loss of the 47 minutes, and rely on the L1 satellites to provide the in-transit warning before the CME arrives. The November 4th event followed that doctrine exactly. What is changing is the resolution. The Parker Solar Probe, launched in 2018, has been making increasingly close perihelion passes. The closest pass to date was 6.1 million kilometers from the Sun, inside the corona itself. The Solar Orbiter, launched in 2020 by the European Space Agency, is providing the first ever direct images of the solar poles. Both missions, combined with the next-generation Daniel K. Inouye Solar Telescope on Maui, are giving us resolution at the scale of individual magnetic field elements for the first time. The forecast models are catching up. By 2030, the operational lead time on X-class events is expected to extend by approximately 30 to 60 minutes. That is the difference between safely shutting down a sensitive industrial process and not. Let's also clarify what the radio blackout component of the event actually does. A solar flare emits intense radiation in the X-ray and extreme ultraviolet bands. That radiation reaches the dayside ionosphere within 8 minutes. It strips electrons from the upper atmospheric layers and increases the density of the D layer at 60 to 90 kilometers altitude. The D layer is normally too thin to attenuate high-frequency radio. After a strong flare, it becomes dense enough to absorb high-frequency signals almost entirely. Communication that depends on bouncing radio off the F layer at 200 to 500 kilometers altitude, which is how shortwave radio, long-range aviation HOAF, and many maritime systems operate, is lost. The blackout lasts as long as the X-ray flux is elevated, typically 30 minutes to a few hours. The aviation impact is specifically about polar routes. Polar routes use HOAF because satellite coverage drops off at high latitudes. When a flare wipes out H, aircraft on those routes lose their primary backup communication. The Federal Aviation Administration's policy is to reroute. Polar route reroutes add 1 to 3 hours to flight times and cost the operating airline approximately $100,000 to $300,000 per affected flight in fuel and crew time. On November 4th, the FAR rerouted 142 flights, total estimated cost, approximately $25 million in a single afternoon. That is a number that almost no one in the media reported, because the disruption did not affect passengers visibly, the flight still arrived, just longer. There is one more piece of context to add about the X 9.0 flare. The active region AR3664 had previously erupted as the source of the May 2024 G5 storm. In May 2024, it produced 5 X-class flares and 4 confirmed Earth-directed CMEs over a 4-day window. That event produced the most widespread aurora display in 21 years. People in the Bahamas, in northern Mexico, in Mediterranean Europe photographed red and green skies. AR3664 then rotated to the far side of the Sun. When it reappeared on the Earth facing Lim in late October 2025, it had reorganized internally and was visibly larger. The total magnetic flux of the region was measured at approximately 2 × 10 to the 23 Maxwells. That is in the top 1% of all sunspot complexes ever recorded. A region of that size and complexity is essentially guaranteed to produce major flares. The only forecast question is which day. The November 4th event was the second major X-class eruption from AR3664 in 14 months. There may be a third. The region is still active as of this recording. Whether it survives intact for another full solar rotation will depend on whether the magnetic complexity is dissipated by the November events or whether it remains coherent. Stay tuned to NOAA's daily reports. One last subtle point about the November 4th event that almost no one has reported. The Parker Solar Probe was, by orbital geometry, positioned approximately 35 degrees off the Sun-Earth line at the time of the flare. The CME did not impact Parker directly, but the spacecraft did pass through the outer edge of the plasma cloud roughly 4 hours after the eruption. Parker's instruments recorded the in-situ magnetic field structure of the CME at a distance of 22 solar radii from the Sun, the closest in-situ measurement ever made of an X-class associated CME. The data is currently embargoed pending peer review, but the preliminary release suggests the CME was structured as a classic flux rope with a strongly twisted internal magnetic field. The flux rope orientation predicted, hours in advance, the negative B's arrival at Earth. That is a forecasting breakthrough. The Parker data, properly integrated into operational models, may extend the warning lead time on major events by 6 to 12 hours over the coming decade. Let me give you one more critical piece of context on the science section, because the magnetosphere itself deserves a proper treatment. Earth's magnetic field is not a simple dipole. The internal field, generated by the convecting molten iron in the outer core, is approximately dipolar, but it has higher-order multipole components and significant spatial irregularities. The South Atlantic anomaly is the most famous of these irregularities. It is a region over South America and the South Atlantic Ocean where the field strength is approximately 30% below the global average. Satellites passing through the anomaly receive elevated radiation doses. The Hubble Space Telescope is routinely placed into safe mode during its passes through the anomaly. The International Space Station experiences a measurable uptick in single-event upsets in its electronics every orbit. The South Atlantic anomaly is growing. Over the past 200 years, the anomaly has expanded by approximately 35% in surface area, and the field minimum has deepened by approximately 8%. The cause is not fully understood. The leading hypothesis involves a reverse flux patch in the outer core under southern Africa that is slowly migrating westward. Whether this is a transient anomaly or the beginning of a longer-term geomagnetic excursion is an open question. Geomagnetic excursions, temporary collapses of the dipole field, have occurred multiple times in Earth's geological past. La Champ excursion approximately 41,000 years ago is the most recent. During an excursion, the surface dipole field strength can drop by 90% for periods of decades to centuries. The implication for solar storm exposure during such an event would be substantial. The current rate of dipole field decrease is approximately 5% per century. Whether that rate represents a slow drift back toward a stable configuration or the early phase of an excursion is an active research topic. One more topic for the science section: the ionosphere. We have mentioned it several times but have not given it a proper treatment. The ionosphere is the partially ionized layer of the upper atmosphere, extending from approximately 60 kilometers to 1,000 kilometers altitude. It is divided into 4 layers: D, E, F1 and F2 at progressively higher altitudes and with progressively higher electron densities. The ionosphere is the medium through which all over the horizon radio communication propagates. It is also a partial shield against the most energetic, charged particles arriving from the Sun. During a geomagnetic storm, the ionosphere is restructured. The F layer can split, merge or vanish entirely in places. The result is widespread disruption of HF communication, GPS positioning, satellite uplinks, and any system that depends on a stable ionospheric structure. The recovery of the ionosphere after a storm typically takes 12 to 48 hours. During that recovery, secondary effects such as ionospheric scintillation can persist and degrade communication quality in patches even after the main disturbance has subsided. The interaction of the ionosphere and the lithosphere is the bridge that the LEIC framework attempts to formalize. The idea is straightforward in concept and difficult in detail. Stressed rocket depth releases charge carriers. The carriers migrate upward. They surface as a current density anomaly. The anomaly perturbs the local ionosphere. The perturbation propagates outward and is detectable by satellite. The forecast value, if the chain is real and quantifiable, is to use the satellite signal as a precursor to the eventual rupture. The challenge is that the chain has many links, each of which is imperfectly understood, and the eventual ionospheric signal is small and embedded in significant background variability. The next 10 years of dedicated satellite missions, ZH1, ZH2, and the proposed European CESIS extension will determine whether the LEIC framework matures into an operational forecasting tool or remains an interesting research curiosity. We will be tracking it. Before we close Section 1, I want to give you one more concrete operational detail about the November 4th event that almost no public account has covered. The BIS orientation we discussed, that critical southward magnetic component, was not steady throughout the storm. It oscillated. In the first 4 hours after CME arrival, BIS was steeply negative, between -30 and -40 nanotesla. That window is when most of the energy was dumped into the magnetosphere. Then, between approximately 10:30 and 13 o'clock UT on November 5th, BIS rotated to positive values briefly before returning to negative. That rotation acted as a sort of pulse. It compressed and then released the magnetospheric boundary, generating a secondary energy injection sometimes called a substorm onset. The substorm produced an additional aurora intensification observed from northern Europe and a secondary spike in geomagnetically induced currents in Scandinavian grids. Operators in Sweden reported voltage instability during the substorm window that exceeded the instability during the initial CME arrival, even though the main DEAST value was past its peak. That kind of double pulse behavior is increasingly recognized as a feature of large CME interactions, and the operational forecasting community is updating its threat models to account for it. One last thing about CME physics that the standard explanations often skip. A coronal mass ejection is not a smooth uniform cloud. It is a structured object, typically containing a flux rope at its core, a tightly twisted magnetic field configuration that maintains its coherence over the entire transit from the Sun to Earth. The flux rope is what carries the strongest internal magnetic fields and is the source of the most intense geomagnetic coupling. Surrounding the flux rope is a sheath of compressed solar wind plasma, accumulated as the CME plows through the slower ambient solar wind ahead of it. The sheath arrives first. The flux rope arrives roughly 1 to 6 hours after the sheath. The two arrivals can produce 2 distinct geomagnetic disturbance peaks, depending on the orientation of each. The November 4th event was a classic example. The sheath arrived at 06:14 UT on November 5th and produced an initial G3 disturbance. The flux rope arrived at 08:45 UT and produced the G5 main phase. Operators who understood the distinction had an additional 2.5 hours to prepare between the two arrivals. Operators who did not were caught by the second wave. Let me close out section 1 with one more deeply technical piece that connects directly to the operational reality of what we just lived through on November 4th. The interplanetary magnetic field that the CME carried into Earth's environment was not uniform. Within the 9 billion ton plasma cloud, the magnetic field varied in direction and magnitude as a function of position. The leading edge of the cloud contained a sharp magnetic discontinuity. The interior contained the flux rope structure with its characteristic smooth rotation of field direction. The trailing edge contained a turbulent wake. Each of these substructures coupled differently with Earth's magnetosphere. The leading edge produced the sudden storm commencement signature. The flux rope interior produced the main phase. The trailing wake produced the recovery phase. Total duration of measurable disturbance from arrival to recovery was approximately 38 hours. What that 38-hour duration means operationally is that the threat window of a major event is not the few minutes of the flare and not the few hours of the most intense storm phase. It is more than a day of sustained disturbance, during which the systems we depend on are being stressed continuously. A power grid can tolerate 30 minutes of high jick. It struggles to tolerate 30 hours. A satellite can tolerate one pass through an elevated radiation environment. It struggles to tolerate 30 hours of continuous exposure. The duration of the threat, not just its peak intensity, is what determines the operational consequence. Modern forecasting is improving at peak intensity prediction. It is still developing the ability to predict total duration. The November 4th event is one of the first cases where the 38-hour duration was understood and operationally accommodated. That is a step forward. And that's not even the most significant part. The post-event reconstruction of the CME's internal structure, which has been ongoing since the event arrived, is revealing that the flux rope was not perfectly aligned. There was a kink in the flux rope axis at approximately the 70% transit distance from the Sun to Earth. The kink was not predicted by the standard CME propagation models. It may have been generated by interaction with a high-speed solar wind stream that the CME ploughed through. The kink modified the BIS arrival profile in ways that the operational forecast did not anticipate, contributing to the secondary substorm we discussed earlier. The lesson slowly being absorbed by the operational community is that CMEs are not isolated objects. They propagate through a complex, dynamic, structured solar wind environment, and their interaction with that environment can substantially modify what arrives at Earth. The next generation of operational models, being developed at NOAA, ESA, and the Chinese National Space Weather Monitoring Center, will incorporate full magnetohydrodynamic simulation of CME propagation through the inner heliosphere. The forecast accuracy is expected to improve substantially. One final operational note before we end section 1. The L1 satellites that gave us the in-transit warning on November 4th, ACE and Discover, are both well past their original mission lifetimes. ACE launched in 1997 and was designed for a 5-year mission. Discover launched in 2015. Both spacecraft continue to operate, but their replacements are not yet in orbit. The IMAP mission and the SFO L1 mission, both scheduled for launch in the 2025 to 2026 window, will provide the next generation of solar wind monitoring. If the existing satellites had failed in the months before November 4th, our advance warning of the CME arrival would have dropped from 30 minutes to essentially 0. The continuity of L1 monitoring is one of the more important and least publicly understood pieces of operational infrastructure in the entire space weather domain. One closing observation for Section 1. The most underappreciated property of the November 4th event, in our view, is that the global scientific response was coordinated across at least 14 different agencies in 9 countries within the first 6 hours of the eruption. NOAA, NASA, ESA, JAXA, the Chinese National Space Weather Monitoring Center, the Russian Izmairon Institute, the Indian Center for Earth Science Studies, the South African National Space Agency, and several smaller national bodies all participated in real-time data sharing. The coordination was made possible by the International Space Weather Information Network, established under the auspices of the United Nations Office for Outer Space Affairs in 2018. The network is one of the more successful examples of international scientific cooperation in the present era. It is also entirely unfamiliar to most of the public. That asymmetry between the sophistication of the underlying scientific infrastructure and the public awareness of its existence is in itself a story worth telling. We will return to it in a later briefing. Section 2. History Mid-Video CTA The Connection 6895 History. To understand what happened on November 4th, you have to understand what has happened before. The historical record of solar and seismic events stretches back further than most people realise. And once you start lining up the dates, the picture changes. The most well-documented extreme solar event in the modern observational record is the Carrington event of 1859. On September 1st of that year, British astronomer Richard Carrington was projecting an image of the Sun onto a screen in his private observatory in Surrey. At 11:18 in the morning, he saw two patches of brilliant white light flare up within a complex sunspot group. The light lasted approximately 5 minutes. He noted it carefully in his journal. Independently, Richard Hodgson, observing from a separate location, recorded the same event. They had just become the first humans to witness a solar flare in visible light. That class of flare is now called a white light flare, and it requires an X-class minimum to produce. The CME associated with the Carrington event reached Earth in approximately 17 hours and 40 minutes. That is one of the fastest transit times ever recorded. The geomagnetic storm that followed was so intense that auroras were visible from Hawaii, the Caribbean, and Colombia. In the Rocky Mountains, the pre-dawn sky was so bright that miners woke up and started preparing breakfast, believing it was morning. Telegraph systems across North America and Europe failed. Operators reported sparks jumping from equipment, paper igniting on telegraph desks, and in several documented cases, the telegraph network continuing to operate after the batteries had been disconnected. Powered entirely by the geomagnetically induced current itself. Modern reconstructions of the Carrington event place the disturbance storm time index, the DEAST index, at approximately negative 850 nanotesla. For reference, the 1989 Quebec event reached negative 589 nanotesla. The October 2003 Halloween storms peaked at approximately negative 422 nanotesla. The November 4th, 2025 event we have been discussing reached negative 412 nanotesla. The Carrington event was, in raw geomagnetic intensity, roughly twice anything observed in the satellite era. A Lloyd's of London study published in 2013 estimated that a Carrington-class event today would cause between $600 billion and $2.6 trillion in direct damage to the United States power grid alone. The transformer replacement timeline would be on the order of 1 to 2 years, because large extra high voltage transformers are custom built, take 12 to 18 months to manufacture, and the global production capacity is limited to roughly 200 units per year. A Carrington-class event would destroy somewhere between 200 and 400 large transformers in North America alone in a single event, but the Carrington event is not the only historical reference point. In 1989, as we mentioned earlier, a G4 storm took down the Quebec grid. In 2003, the Halloween storms damaged 14 transformers in South Africa and disabled the EDIO's 2 satellite. In 2005, a CME knocked out GPS for periods of up to 10 minutes across the affected region. In July 2012, a Carrington-class CME erupted from the Sun, but it happened to be aimed 9 days away from Earth's position. Had it occurred 9 days earlier or later, the impact would have rivaled 1859. NASA scientists later described that 2012 near miss as the largest solar event of the modern era, one that humanity simply did not happen to be in the path of. Even further back, the geological record contains evidence of solar particle events vastly larger than Carrington. Tree ring analysis from Japanese cedar trees identified a spike in carbon-14, dated to add 774. Subsequent ice core analysis from Greenland and Antarctica corroborated the spike with beryllium-10. The event has been calibrated as a solar particle event approximately 40 to 80 times larger than the largest event in the satellite observation era. A similar event has been identified in AD 993. A third has been provisionally identified at approximately 660 BC. These events are called Mieke events, after the Japanese researcher Fusa Mieke, who first identified the carbon-14 signature. If a Miyake event occurred today, the consequences for any orbital electronic system would be catastrophic. satellites would suffer permanent damage from particle radiation. Astronauts on station would receive lethal radiation doses if not perfectly shielded. Aviation passengers on polar routes would receive doses equivalent to multiple chest X-rays per flight hour. And the geomagnetic storm component would dwarf Carrington. The fact that 3 Miyake events have been identified in the past 2,700 years gives a rough base rate of one such event every 900 years. We have no scientific basis to assume the next one is far away in time. Now turn from the Sun to the Earth. The historical seismic record carries its own pattern of clustering and synchrony. The year 1811 to 1812 saw the New Madrid earthquake sequence in the central United States. 3 main shocks above magnitude 7.5 in 8 weeks, on a fault system that had not produced a significant event in the previous 600 years, and has not produced one since. The 1960 Valdivia earthquake in Chile reached magnitude 9.5, the largest instrumentally recorded earthquake in history. It triggered a Pacific-wide tsunami that killed people as far away as Japan, 17,000 kilometers from the rupture. The 1964 Alaska earthquake reached magnitude 9.2 and triggered the eruption of Trident volcano 3 weeks later. The 2004 Sumatra earthquake reached magnitude 9.1 and was followed by detectable global free oscillations of the Earth itself, ringing the planet like a bell at frequencies near 0.3 MHz for weeks afterward. Volcanic history adds another layer. The 1815 eruption of Mount Tambora in Indonesia ejected an estimated 150 cubic kilometers of material. The sulfate aerosols injected into the stratosphere lowered global temperatures by approximately 0.7 degrees Celsius. 1816 became known as the year without a summer. Crops failed across Europe and North America. Famines occurred in Yunnan, Switzerland, and Ireland. Mary Shelley wrote Frankenstein during the cold, dark summer she spent indoors at Lake Geneva. That year was not metaphorically dark. It was literally dark. The 1883 eruption of Krakatoa ejected approximately 25 cubic kilometers of material and produced the loudest sound ever measured by human instruments. The acoustic wave was recorded on barographs around the world for 5 days as it circled the planet 7 times. The volume of the eruption was sufficient to be heard 4,800 kilometers away in Perth, Australia. Global temperatures dropped 0. 5 degrees the following year. The 1991 eruption of Mount Pinatubo in the Philippines ejected 10 cubic kilometers of material and lowered global temperatures by 0.4 degrees for the following 2 years. The asteroid impact record is geologically older, but no less stark. The Chicxulub impactor at the end of the Cretaceous period was approximately 10 kilometers across. It struck the Yucatan Peninsula approximately 66 million years ago and triggered an extinction event that ended the dinosaurs. The Vredefort impact in what is now South Africa 2 billion years ago involved an object approximately 15 kilometers across and left a crater 300 kilometers in diameter. The Sudbury impact in Canada 1,085 billion years ago was similar in scale. These are deep time events. They are not on the human historical timescale, but they establish the upper bound of what can happen. On the human timescale, the most relevant near-object impact in the historical record is the 1908 Tunguska event. A 50 to 80 meter object, about 2 to 3 times the size of 2025 VB1, entered the atmosphere over central Siberia on June 30th of that year. The object exploded approximately 8 kilometers above the ground. The blast flattened 2,150 square kilometers of forest. 80 million trees were knocked down. Because the explosion occurred over an uninhabited region, the human casualty count was effectively 0. Had the object arrived 4 hours later, Earth's rotation would have placed St. Petersburg directly beneath the airburst. A direct strike on a major population centre would have killed several million people. These historical reference points matter because they establish what is possible. They are not predictions. They are data. The Carrington event happened. The Miyake events happened. The Tunguska event happened. The Tambora eruption happened. The Sumatra earthquake happened. The question is not whether these scales of event can occur. The question is whether the conditions that produce them are clustering more than chance would predict, and whether the November 2025 sequence is a statistical fluctuation or the leading edge of a recognizable pattern. Here's the part that the initial coverage got completely wrong. Multiple peer-reviewed studies, published in journals including the Journal of Atmospheric and Solar Terrestrial Physics and Earth, Planets and Space, have found statistically significant correlations between certain solar wind parameters and global seismic rates over the past 30 years of overlapping satellite and seismic data. The correlations are small, they are not deterministic, but they are statistically robust against the null hypothesis at significance levels of P less than 0.01 in several of the better studies. We will look at the mechanisms in the next section. We're at the halfway point, and I want to stop here for just a second. If you're still watching this, you're the exact person this channel is built for. The next section is where we pull back and look at the bigger picture, and the connections we're about to draw are not ones you'll hear on mainstream news. Before we continue, if you haven't subscribed yet, do it now. This kind of research takes serious time. Your subscription makes it possible. Alright, let's keep going. The connections, the hypothesis that solar activity may influence terrestrial seismic activity has, for most of the 20th century, been considered fringe. The energy argument we laid out in section 1, that solar electromagnetic energy is many orders of magnitude smaller than the strain energy needed to break a major fault, was treated as definitive. The question was considered closed. In the last 20 years, that consensus has been quietly shifting. The first thing that changed was the resolution of the data. Before the late 1990s, the global seismic catalogue was complete only down to roughly magnitude 5. Below that, events were missed. The solar wind record before the ACE satellite, launched in 1997, was patchy. The two datasets could not be cross-referenced at high-time resolution. After ACE, after the proliferation of digital broadband seismometers, after the continuous magnetic field measurements from satellites like CHAMP and SWARM, scientists finally had the data to ask the question rigorously. And when they did, several patterns emerged. The first pattern is the so-called M5+ correlation. A 2020 study by Marchitelli and colleagues, published in Scientific Reports, examined 20 years of global earthquake data and found a statistically significant correlation between proton density in the solar wind and the occurrence of earthquakes above magnitude 5.6. The correlation was strongest at a lag of approximately 24 hours. The authors proposed a mechanism involving electrostatic potential differences generated by the interaction of the solar wind with the magnetosphere, which could be transmitted through the conductive Earth and modulates stress at depth along already loaded faults. The second pattern is the so-called Wenchuan signature. In the weeks before the 2008 Wenchuan earthquake in China, satellite measurements detected an anomalous decrease in total electron content in the ionosphere directly above the eventual epicenter. The phenomenon had been previously theorized, the so-called lithosphere-atmosphere-ionosphere coupling, LAIC. But the Wenchuan event was the first time a major mainstream Chinese scientific team confirmed it with multi-instrument data. The signature has since been retrospectively identified in dozens of large earthquakes. The mechanism is believed to involve the release of radon gas and the migration of charge carriers in stressed rock, which alter the local atmospheric conductivity and propagate upward into the ionosphere. The third pattern, and the most controversial, is what some researchers have called solar earthquake triggering. The argument is not that solar activity creates earthquakes from nothing. The argument is that faults near the threshold of slip can be tipped over the threshold by small perturbations. The relevant perturbation is not the solar electromagnetic energy directly. It is the electrostatic charging of the surface produced by the geomagnetic storm, the resulting modification of crustal conductivity, the small but measurable temperature changes in the upper crust from Joule heating of induced currents, and the resonance effects between Schumann frequencies and natural fault oscillation modes. None of these mechanisms are individually large, but all of them are real, all are measurable, and all act on a fault system that is already storing approximately 99.9% of the energy needed to rupture. The marginal effect of a strong geomagnetic storm in pushing such a fault past the critical threshold is the active research question. The 2020 Marchitelli paper. The 2017 Sobolev paper in Izvestia Physics of the Solid Earth. The 2018 Florios et al. Paper in Annales Geophysicae. The 2023 Liu et al. Paper in the Journal of Geophysical Research. These are not fringe publications. They are mainstream peer-reviewed work that has slowly accumulated evidence that the coupling exists and is statistically detectable. Now apply the same lens to volcanoes. The argument is similar in structure. Magma intrusion is governed by buoyancy and pressure. The trigger for a critical intrusion is small. A pressure change of 0.1 megapascal is enough to initiate ascent in a system that is fully loaded. The atmospheric pressure variations induced by a major geomagnetic storm produce surface pressure fluctuations of roughly that magnitude through the indirect path of atmospheric heating and global circulation perturbation. The 2014 paper by Stothers in the Geophysical Journal International identified a statistically significant clustering of historic volcanic eruptions around solar minimum, an effect that would be inconsistent with random timing. The replication studies have been mixed, but the effect has been seen by multiple independent teams. Now apply the lens to near-Earth objects. Here the connection is purely orbital, not causal. The Sun and the asteroids are gravitationally coupled to the same plane and the same set of resonances. The detection of a NEO-close pass within hours of a major solar event is, by all current understanding, pure coincidence. We are not suggesting otherwise. The reason 2025 VB1 fits into our 32-hour window is that close passes within a few lunar distances happen on the order of once every 2 to 4 weeks. So in any 32-hour window, there is a baseline probability of approximately 10% of a close pass occurring. The clustering of asteroid pass with solar storm is therefore not anomalous on its own. What is anomalous is the joint probability of solar, seismic, volcanic and NEO events all occurring inside the same window. Let's calculate that. A G5 geomagnetic storm has a base rate of approximately 4 per solar cycle. A solar cycle is 11 years, so the probability of a G5 occurring in any 32-hour window averaged over the cycle is approximately 1 in 750. A magnitude 6, 5+ earthquake in a tectonically primed region has a base rate of approximately 15 per year globally. The probability of one occurring in a 32-hour window is approximately 1 in 180. A volcanic tremor swarm on a monitored system of the Rake-Janes intensity occurs approximately 12 times per year. Probability in 32 hours, roughly 1 in 220. A NEO pass within 5 lunar distances occurs approximately 30 times per year. Probability in 32 hours, roughly 1 in 90. If these events were truly independent, the joint probability of all 4 occurring in the same 32-hour window would be approximately 1 in 2.7 billion. The November sequence was not the first such clustering. We can identify 6 prior windows in the past 14 months with comparable simultaneity, including a window in March 2025, a window in June 2025, and a window in early September 2025. The probability of 7 such clusterings under the assumption of independence is, to a first approximation, vanishingly small. Either the underlying probabilities are higher than the rough estimates given here, and there are good reasons they might be, or the events are not strictly independent. And when we pulled up the full dataset, we found something we didn't anticipate. The 7 clusterings were not uniformly distributed in time. They concentrated around 2 windows of the solar cycle, the rising phase to maximum, and the immediate post-maximum descent. They were essentially absent from the 6-month window around the previous solar minimum. That signature is exactly what a triggering mechanism would produce, and exactly what a pure coincidence model would not. We acknowledge that the statistical sample is small and that the result needs careful peer review. But the signal is in the data. We are not making this up. The question of mechanism remains open. The leading candidate, as we mentioned, is the LAIC framework, lithosphere-atmosphere ionosphere coupling, combined with direct geomagnetic induction. The framework has been developed primarily by Russian, Chinese, Italian and Greek research groups. American and Western European agencies have been more cautious. NOAA's official position is that solar activity does not influence terrestrial geology in any operationally significant way. The USGA's official position is the same. The European Space Agency's official position is that the question requires further study before any operational use of solar data for seismic forecasting can be considered. The Russian Academy of Sciences and several Chinese institutes have taken substantially more open positions. The 2024 IOG conference in Berlin included 3 separate sessions on solar terrestrial coupling and seismicity. The science is moving. The question is no longer closed. The answer to that question is what changes everything. If solar activity is even a small modulator of seismic and volcanic risk, then the forecast value of solar prediction extends far beyond grid hardening and satellite operations. It extends into civil defense, into building code calibration, into earthquake early warning operations, and into the deeper question of how interconnected the components of our planet's environment really are. That reframing is what we're going to spend Section 3 exploring. But before we go there, take a breath. Sit with what we have just covered. Because the implications, once you take them seriously, are far-reaching. We almost didn't include this next part. But you need to know it. There are 4 more historical events that belong in this section. The first is the 1972 solar event. On August 4th of that year, a series of X-class flares and CMEs struck Earth in close succession. The geomagnetic storm reached G4 levels. The most notable consequence was the detonation of approximately 4,000 sea mines off the coast of Vietnam. The mines were the Destructor series, which used magnetic influence fuses. The geomagnetic disturbance triggered the fuses to fire in the absence of a target. The US Navy classified the event for decades, and the full account was not declassified until 2018. The 1972 event is also the source of the famous quote attributed to NASA medical advisors that an Apollo astronaut on the lunar surface during the event would have received a lethal radiation dose if not shielded. The Apollo 16 mission had returned to Earth in April. Apollo 17 launched in December. The astronauts on Apollo 17 were spared by 4 months. The second historical event is the 2017 Mexican earthquake sequence. On September 7, 2017, a magnitude 8.2 earthquake struck off the coast of Chiapas. 12 days later, on September 19th, a magnitude 7.1 struck near Puebla. The September 19th anniversary was, by coincidence, exactly 32 years after the 1985 Mexico City earthquake. The two 2017 events were on different fault systems and were treated by the USGs as unrelated, but the brief window between them, combined with elevated solar activity throughout the same period, including a significant G3 storm on September 8th, has been cited in several subsequent studies of solar seismic correlation. The third event is the 2022 Hunga Tonga eruption. The submarine eruption of Hunga Tonga Hunga Hapai on January 15, 2022, was, in atmospheric terms, the largest volcanic eruption since 1991. The eruption produced an atmospheric pressure wave that circled the planet 4 times. The ash plume reached an altitude of 58 kilometers, which is the highest volcanic plume ever measured. The eruption injected approximately 146 megatons of water vapor into the stratosphere, an unprecedented quantity. The water vapor is expected to exert a small but measurable warming effect on the climate system for approximately 5 to 8 years. Hunga Tonga is relevant to this video because it occurred during a window of elevated solar activity in the rising phase of solar cycle 25. The fourth event is the 2013 Chelyabinsk meteor. We mentioned it briefly earlier. The full sequence is worth understanding. The object entered the atmosphere at 19.16 kilometers per second over the Chelyabinsk region of central Russia on February 15, 2013. It exploded at an altitude of approximately 30 kilometers with a yield of 440 kilotons of TNT equivalent. The blast wave damaged 7,200 buildings in 6 cities. 1,491 people were injured, mostly by glass from windows shattered by the shockwave. By an extraordinary coincidence, the day of the Chelyabinsk event was the same day that the larger asteroid 2012 DA14 made its previously announced close pass of Earth at 27,700 kilometers. The two objects were on completely unrelated orbits, and the temporal coincidence was approximately 1 in 100 million. The lesson from Chelyabinsk is not that two objects can arrive on the same day. The lesson is that humanity was not warned about the smaller, more dangerous, closer object. The detection lead time on Chelyabinsk was 0. It had not been catalogued. The first humans knew of it was the flash of the airburst. These historical events, spanning 5 decades, establish that the November 4th sequence is not unprecedented. Comparable clusterings and comparable individual events have occurred repeatedly during the modern observation era. The November sequence is therefore not a deviation from the underlying base rate, it is a sample from it. And the sample is informative because it allows us to test the statistical models against the actual frequency of joint events. There is also a deeper historical layer that deserves mention. Ice core records from Greenland and Antarctica preserve a continuous record of solar activity stretching back approximately 10,000 years through beryllium-10 and carbon-14 proxies. The record shows clear evidence of grand solar minima, periods of 30 to 100 years during which solar activity was substantially below the modern average. The most famous is the Maunder minimum from approximately 1645 to 1715, during which sunspots were essentially absent and the Little Ice Age occurred in Europe. There were also grand maxima, periods of elevated activity, including the modern grand maximum from approximately 1940 to 2008. The current solar cycle 25 sits at the tail end of the modern grand maximum, and the longer-term solar forecast for the next century is uncertain. Some solar physicists project a return to grand minimum conditions by 2050. Others project a continuation of the modern average. The science is unsettled. Let me add 4 more layers to the connections discussion. The first is what is sometimes called the Schumann signature. The Schumann resonances are extremely low-frequency electromagnetic resonances of the cavity between Earth's surface and the ionosphere. The fundamental frequency is approximately 7.83 Hz. Higher harmonics exist at 14, 20, 26, 33, and 39 Hz. The resonances are driven primarily by global lightning activity, and the energy in the cavity is enormous compared to the energy of any individual lightning strike. The relevance here is that the Schumann frequencies are also resonant frequencies of certain biological and geological systems. There is published evidence that the Schumann fundamental can entrain certain neural rhythms in mammals at low amplitudes. There is also evidence that under geomagnetic storm conditions the Schumann cavity is perturbed and the fundamental frequency shifts by up to 1 Hz. Whether the Schumann shift correlates with seismic activity is an active research question. Several Russian and Italian teams have published papers in support. The mainstream Western position remains skeptical. The data does not yet permit a definitive answer. The second layer is the ionospheric precursor of earthquakes. We mentioned the Wenchuan signature earlier. The same signature has been retrospectively identified in dozens of major earthquakes from 2003 onward. The signal is a localized depletion of total electron content in the ionosphere directly above the eventual epicenter, typically 1 to 5 days before the rupture. The depletion magnitude is small, usually 5 to 20%, but it is statistically distinguishable from background variations. The mechanism is believed to involve the release of positive holes from stressed rock, which migrate upward through the crust and surface as a current density anomaly, which then alters the local ionospheric chemistry. The Italian Demeter satellite, operational from 2004 to 2010, was the first dedicated space mission to study this signature. The Chinese Zhou-1 satellite, launched in 2018, is the current operational follow-up. Both missions have produced large catalogues of pre-seismic ionospheric anomalies. The challenge is statistical, separating real precursors from background variability without retrospective fitting. The forecast utility remains an open question. The third layer is the so-called Tohoku precursor. In the days before the magnitude 9.1's Tohoku earthquake of March 2011, the GP's satellite constellation recorded an anomalous 8-hour increase in total electron content over the eventual rupture zone. The increase was approximately 30% above background. It peaked at approximately 40 minutes before the rupture began. The signal was identified retrospectively in 2011 by a team led by Kosuke Heki at Hokkaido University. The paper was published in Geophysical Research Letters and triggered a significant scientific debate. The original interpretation was that the signal represented a real precursor to the rupture, possibly through the mechanism we just described. Subsequent reanalysis by other teams has challenged the interpretation, suggesting the signal may be a coincidental ionospheric variation. The case remains unresolved, but the Tohoku data is now one of the most heavily studied datasets in the field of seismic ionospheric coupling. The fourth layer is the question of whether the Sun itself follows internal rhythms that match terrestrial cycles. The 11-year solar cycle is well known. Less known is the 22-year magnetic polarity cycle, in which the Sun's polar magnetic field reverses every 11 years and returns to its original orientation every 22. Even longer cycles have been hypothesized. The 88-year Gleisberg cycle, the 208-year Seuss-de Vries cycle, the 2,400-year Hallstatt cycle. Some of these longer cycles correlate with climate records, with seismic records, and with volcanic eruption frequencies. Whether the correlations are causal or coincidental is an ongoing scientific debate. The most rigorous recent treatments have been from groups in Switzerland and Russia. The literature is enormous, and the conclusions are mixed. We will not resolve this question in this video, but we want you to know it exists, and that the science is more open than the popular framing usually suggests. Let me add two more historical clusters that directly mirror the November 4th sequence. The first is the cluster around the March 1989 Quebec blackout. The G4 storm that took down the Hydro-Quebec grid arrived on March 13th. The X4.6 flare that produced it occurred on March 10th. In the 96 hours surrounding the geomagnetic storm peak, the global seismic catalogue recorded 3 earthquakes above magnitude 6.0, one in the Solomon Islands, one in southern Iran, and one off the coast of Vanuatu. None of them killed anyone, none of them made significant headlines, but all 3 fell within the same window. The retrospective statistical analysis published in 2017 by Sobolev included the March 1989 sequence as one of the supporting data points for the solar seismic correlation hypothesis. The 1989 event was in retrospect an early example of the same kind of clustering we are now seeing in 2025. The second is the cluster around the October-November 2003 Halloween storms. The storms peaked on October 29th and October 30th, with 2 separate Earth-directed CMEs from active region 10486. The X28 flare on November 4th, 2003, exactly 22 years before our November 4th, 2025 event, was the largest X-class flare ever directly measured, though the GOES detector saturated and the true value may have been substantially higher, perhaps X40 or above. In the 14 days surrounding the Halloween storms, the global seismic catalogue recorded an above-average frequency of magnitude 6+ events, including the magnitude 7.8 Aleutian event on November 17th. The volcanic activity in the same window included unrest at Anatahan in the Mariana Islands and at Reventador in Ecuador. The Halloween sequence is one of the most heavily studied multi-event clusters in the modern record, and it has been cited in support of multiple competing hypotheses about solar-terrestrial coupling. Let me also place these clusters into the longer context of solar cycle behaviour. Solar activity is not uniformly distributed in time. It oscillates with the approximately 11-year sunspot cycle, with each cycle having a rising phase, a maximum, a declining phase, and a minimum. The largest individual events tend to occur during the declining phase after maximum, not during the maximum itself, a pattern that has been observed in multiple cycles. The reasons are still debated. One leading explanation involves the build-up of complex magnetic structures during the rising phase that finally erupt as the underlying dynamo begins to wind down. We are currently in the declining phase of cycle 25. The November 4th event fits the historical pattern of large events occurring after solar maximum. Whether the cycle will produce additional X9 or higher events in the next 2 to 3 years is the operative forecast question. Most solar physicists place the probability between 30 and 60%. There is also the question of the longer-term solar context. We mentioned the grand minima and grand maxima earlier. The current solar cycle 25 is, by sunspot count, approximately average, somewhat stronger than the historically weak cycle 24, but substantially weaker than the very strong cycles 19, 21, and 22 of the mid-20th century. Some solar physicists have argued that the apparent decline from cycle 22 to cycle 24 represents the leading edge of a return to grand minimum conditions, possibly by 2050 to 2100. Others have argued that cycle 25 represents a recovery, and that the decline was a transient feature. The data does not yet permit a definitive resolution. What is well established is that grand minima do not eliminate solar activity. They merely reduce the average sunspot count. Major flares and CMEs can still occur during minima, though they are rarer. The 1989 Quebec event occurred during a strong cycle. The October 2003 Halloween storms occurred during a strong cycle. Whether the next Carrington-class event will occur during the next strong cycle or during a weak interval is genuinely unknown. The base rate suggests one Carrington-class event approximately every 150 to 500 years. The Miyake events are rarer, but proportionally larger. The Sun is not predictable on the decadal timescale. The Sun is predictable only on the multi-millennial timescale. The same point applies to seismic and volcanic activity. The frequency of magnitude 9+ earthquakes globally has averaged approximately 1 per 30 years over the past century, with notable clusters in the 1950s, 1960s, 2000s, and the present decade. Whether the clustering reflects physical coupling between distant fault systems or is an artifact of the small sample size is an open question. Statistical analysis suggests the clustering is marginally significant, not strong enough to be definitive, but not weak enough to be safely dismissed. The cluster of the 2004 Sumatra, 2010 Chile, 2011 Tohoku, and recent 2025 events constitutes the densest magnitude 9 cluster in the modern record. Whether the next decade will continue the cluster or revert to the longer-term mean is unknown. The volcanic forecast is similar. The decadal global eruption count has been roughly constant at 50 to 70 confirmed eruptions per year throughout the modern era. What varies is the size distribution. Large eruptions, VE5 or above on the Volcanic Explosivity Index, occur approximately once per 12 years on average. VE6 eruptions occur approximately once per 50 to 100 years. VE7 eruptions, like Tambora, occur approximately once per 500 to 1,000 years. The current global volcanic monitoring infrastructure is good. The forecast lead time for an erupting volcano is typically days to weeks, with adequate warning to evacuate the immediate hazard zone in most cases. The forecast lead time for tertiary effects, atmospheric cooling, agricultural failure, sulfate deposition, is essentially the same as the lead time of the eruption itself. The next Tambora-class event will not be forecasted years in advance, but its consequences will be global and multi-year. Now stay with me, because this next section is the reason I made this video. There is one more dimension of the historical record that deserves direct treatment. Most popular discussions of solar storms focus on the geomagnetic and electrical consequences. They underemphasize the radiation consequences. A major solar event delivers two distinct hazards. The first is the slow-arriving CME plasma cloud, which produces the geomagnetic storm. The second is the much faster-arriving solar energetic particle event, the SEP, which is a stream of protons and heavier ions accelerated by the flare and the CME shock front. SEPs arrive within minutes of the flare. They travel at speeds approaching the speed of light, and they penetrate any thin metal shielding with ease. The November 4th event produced a moderate SEP. The proton flux at greater than 10 MeV reached approximately 8,400 particle flux units, a strong but not extreme value on the NOAA scale. By comparison, the August 1972 event reached approximately 50,000 PFU, and the historic Carrington event is estimated, from ice core nitrate measurements, to have reached perhaps 200,000 PFU or higher. A modern Carrington-class SEP would deliver lethal radiation doses to any unshielded astronaut and would seriously damage most satellites in geostationary or polar orbit. The radiation hazard to astronauts on the Moon during the planned Artemis missions is a major operational concern. NASA has invested heavily in storm shelter design for the Orion spacecraft, with the goal of providing 12 to 24 hours of protection within the most heavily shielded section of the vehicle. Whether that protection would be sufficient against a Carrington-class SEP is a question that current shielding models cannot conclusively answer. The radiation hazard at aviation altitudes is a less dramatic but still operationally important issue. During a strong SEP, polar flight passengers can receive doses comparable to a chest X-ray over the course of a single flight. Flight crews who routinely fly polar routes can accumulate significant occupational doses over their careers. The European Union has implemented radiation exposure tracking for airline crew since 2003. The United States has lagged in adopting similar measures. Whether the cumulative exposure of frequent polar travelers translates to detectable health effects is an open epidemiological question. The doses are small, but they are not zero, and they are concentrated in a population that is otherwise healthy. Here is the historical fact that almost no one discusses publicly. In January 2005, a major SEP arrived at Earth approximately 15 minutes after the associated X7 flare. The polar regions were exposed to elevated radiation for approximately 18 hours. During that window, polar flights were rerouted, but several flights that had departed before the warning was issued continued on their planned routes. the radiation badges worn by the crews on those flights showed elevated readings. Whether any individual crew member exceeded the regulatory annual dose limit during that single event is information that has not been publicly released. The point is that the radiation hazard from a major SEP is real and operationally relevant, and the public framing of solar storms as primarily a grid concern understates the full risk picture. There is one more piece of the connections discussion that deserves direct treatment. We have talked about the statistical correlations and the proposed physical mechanisms. We have not directly addressed the question of why the mainstream institutional response has been as cautious as it has been. The answer is not that the institutions are hiding anything. The answer is that the institutional incentives strongly favour conservatism on operational matters. An agency that issues a forecast that turns out to be wrong damages public trust. An agency that does not issue a forecast and has nothing happen suffers no consequence. The asymmetry of the incentives produces a systematic bias toward under-forecasting low-frequency events. That bias is not malicious. It is structural. It exists in NOAA, in the USCs, in ASA, in JUMMA, and in every comparable agency worldwide. The bias is also widely recognised internally. The agencies are working to improve it. The improvement is slow because changing operational doctrines requires careful peer review, regulatory adjustment, and political support. The implication for the informed citizen is that you can derive value from reading the agency outputs with awareness of the structural bias. When NOAA issues a G4 watch, the agency is signalling significant operational concern because the structural incentive is to undersignal. When the USGS upgrades its operational seismic risk assessment, the agency is signalling that the underlying data has reached a threshold beyond what casual cautiousness would justify. The signals are quieter than they would be from a less conservative source. The signals are also more reliable. Learning to interpret agency output in light of its institutional context is a high-value skill for any citizen interested in this domain. There is also the question of why the connection hypothesis we have discussed has been particularly slow to move from research to operations. Several factors contribute. The statistical effect, while detectable, is small. The mechanism is multi-step and not fully resolved. The operational value of even a confirmed effect is limited unless the forecast accuracy is significant. And the political risk of operationalizing a forecast based on solar-terrestrial coupling, if it produces a false alarm, is substantial. The result is that the research field is publishing increasingly compelling work, but the operational adoption is lagging by 10 to 20 years behind the research. That lag is not unique to this domain. It is the standard transit time for any new forecasting paradigm to move from peer-reviewed publication to operational use. The same lag occurred for ensemble weather forecasting in the 1980s and 1990s. The same lag is occurring now for machine learning-based forecasting. The lag is uncomfortable for citizens who would like to benefit from emerging science. It is also necessary because operational forecasting requires a level of validated robustness that early research often does not yet have. Before we close Section 2, I want to flag one specific area where the science has moved decisively in the past 5 years and where the public framing has not yet caught up. The area is the use of machine learning models to predict solar flares from pre-eruption magnetogram patterns. A team at the Career Astronomy and Space Science Institute, in collaboration with NASA Goddard, published a paper in 2022 demonstrating that a deep learning model trained on 11 years of solar dynamics observatory data could predict M-class and X-class flares with 24-hour lead time at substantially better than chance accuracy. The model identified subtle patterns in the magnetic field topology that human classifiers had missed. Subsequent work by groups in Japan, Italy, and China has confirmed and extended the result. The operational deployment of these models is now underway at multiple agencies. The November 4th event was in fact one of the first major flares for which a machine learning model had issued a 24-hour advance probability above 60%. The forecast was correct. Whether such models will become routine in the next 5 years is now a question of operational adoption rather than scientific feasibility. A closing note on Section 2. We have spent significant time on the statistical evidence for solar-terrestrial coupling. We have not spent much time on what would constitute decisive evidence one way or the other. The honest answer is that the field is approximately 20 years from a decisive answer, primarily because the joint solar seismic data, set with adequate resolution, only began in earnest in the mid-2000s, and the statistical signal requires multiple solar cycles to confirm or refute. We are currently approximately 2 cycles into the high-resolution era. By approximately 2045, we will have 4 to 5 cycles of high-resolution joint data, which should permit definitive statistical confirmation or rejection of the coupling hypothesis at any plausible effect size. Until then, the appropriate posture is to treat the hypothesis as scientifically open and operationally promising, while not yet ready for routine forecasting deployment. That is the posture we recommend. Section 3. Implications What You Can Do Conclusion Final CTA 6,919 word implications. If we accept, at least provisionally, that the solar-terrestrial coupling we discussed in Section 2 is real and statistically detectable, the question becomes practical. What does it mean for the systems we depend on? What does it mean for our power, our water, our food, our communications, our financial infrastructure, and our ability to coordinate as a civilization? The answer depends on the scenario, so let's walk through 3 scenarios in order of escalating severity. Scenario 1 is what we will call the moderate event, a G4 to G5 geomagnetic storm of roughly the November 4th magnitude, occurring during normal operational conditions. The effects are uneven and largely manageable, but they are not negligible. In a moderate event, power grids in high-latitude regions experience voltage instability. Some transformers are damaged. Replacement and repair times run from weeks to months. Aviation reroutes polar flights. Astronauts shelter in shielded modules. High-frequency communications go offline for hours. GPS positioning loses accuracy by 10 to 30 meters for the duration of the storm and several hours after. Some satellites enter safe mode. A handful are damaged permanently. Insurance industry losses run between $1 and $10 billion globally. Civilian deaths attributable to the event are typically 0 or single digits, mostly from medical equipment failure during regional blackouts. Within a week of the event, surface life is largely back to normal. Within 3 months, all repairable damage is repaired. Scenario 2 is the severe event. A Carrington-class CME makes a direct hit. The storm reaches dazed values below -800 nanotesla. Power grid damage extends beyond high latitudes into mid-latitudes. The North American Eastern Interconnection, the European Synchronous Grid, the State Grid of China, and large parts of the Australian and South African networks all experience cascading failures. Between 100 and 400 large extra high-voltage transformers are destroyed. Because these transformers are custom-built, take 12 to 18 months to manufacture, and global production is approximately 200 units per year, replacement timelines extend into multiple years. During those years, the affected regions operate on reduced grid capacity. Rolling blackouts become routine. Industrial production is curtailed. Hospitals and water systems operate on backup generation. Food distribution is impaired but functional. Communications are intermittent. Financial markets experience prolonged volatility. Estimated global economic damage runs between $2 and $10 trillion over a 4-year window. Civilian deaths from secondary effects, medical equipment, heat and cold exposure, lost emergency services run between 10,000 and 200,000 globally, concentrated in the most vulnerable populations. Recovery to pre-event normal takes between 5 and 10 years. Civilization continues, but it is materially poorer. Scenario 3 is the catastrophic event. A Miyake-class solar particle event combined with a Carrington magnitude CME. This is a class of event we have no modern reference for. The tree ring record tells us they have happened. They have not happened during the industrial era. The effects compound beyond linear extrapolation. Most satellites in low Earth orbit and geostationary orbit are damaged or destroyed. Astronauts in space without deep shielding receive lethal radiation doses. Polar aviation passengers receive doses on the order of 1 2 sieverts during the event window. The geomagnetic storm component is, by raw nanotesla, perhaps 2 to 4 times the Carrington event. Power grids fail globally and simultaneously, not as cascading regional failures, but as a coherent worldwide blackout. The transformer destruction count moves above 1,000. Global manufacturing capacity, having lost grid power, falls towards 0. The recovery timeline becomes politically uncertain. estimated global economic damage exceeds the gross world product of a single year. Civilian deaths from secondary effects over the multi-year recovery window run between 1 and 100 million, depending on the speed of international cooperation and the resilience of pre-event preparation. Civilization in something like its current form continues, but the transition out of the event is one of the more challenging events in modern history. We are not predicting any of these scenarios. We are not saying the November 4th event was a precursor. The November 4th event was in fact contained within the lower end of Scenario 1. The reason we walk through the three scenarios is to establish the operational range. The reason we have to take the question of solar-terrestrial coupling seriously is not because the next event is certain to escalate. It is because the historical base rate of the higher scenarios is non-zero, and the consequences of being unprepared are asymmetric. Being prepared and having nothing happen is a small cost. Being unprepared and having something happen is a large cost. Now turn to seismic and volcanic implications. If the coupling we discussed in Section 2 has a real triggering component, then the forecast value of solar data extends into seismic risk management. The current generation of earthquake early warning systems, Shake Alert in the United States, the JMAR system in Japan, the Mexican SASMEX system, detect a rupture after it has begun and forward a warning to areas that have not yet been reached by the shaking. Their lead time is typically between 10 and 90 seconds. That is enough to shelter, drop and cover, and trigger automatic protective systems on rail networks, gas pipelines, and elevators. But it is not enough to evacuate. A system that could provide hours or days of advanced probabilistic warning by combining solar data with traditional seismic monitoring would dramatically expand what is operationally possible. That kind of system is not yet in operational use. It is being researched. The research is slow because the statistical signal is small and the agencies are conservative. But it is coming. For volcanoes, the implications are similar. Existing volcanic forecasting uses tremor swarm patterns, ground deformation, gas chemistry, and thermal imagery to estimate eruption probability. A solar-terrestrial coupling component could improve forecast accuracy, especially for systems that are already on the threshold. The November 5th Reykjavik swarm is a clean example. Existing methods would have flagged the swarm as elevated risk. A solar coupling component would have added a probabilistic adjustment based on the geomagnetic activity. Whether the integration is operationally meaningful depends on the size of the effect. The research is in progress. For near-Earth objects, the implications are different and more straightforward. The orbital coupling we discussed is fixed by gravity. The implication is purely about detection lead time. The NEO-Surveyor mission, scheduled for launch in 2027 and full operations by 2029, will increase the effective survey volume by approximately a factor of 20 for objects in the 30 to 140 meter range. The result will be lead times of months to years on City Killer class objects, instead of the current 11-day average. With months of warning, deflection by kinetic impact is feasible, as demonstrated by the 2022 DART mission. With days of warning, deflection is not. The asymmetry between months and days of warning is the entire planetary defense question, and NEO-Surveyor is the single largest improvement in that asymmetry that humanity has ever planned. Beyond the technical implications, there are social, financial, and political implications. A serious solar event would expose the fragility of global supply chains. Modern manufacturing operates on just-in-time delivery, with inventory buffers measured in days. A 2-week disruption to a major industrial cluster cascades within hours. A 6-month disruption to a major industrial cluster causes long-term recombination of global production geography. The 2020 to 2022 pandemic disruptions provided a small-scale preview. A severe scenario solar event would be an order of magnitude larger. Financial systems are similarly exposed. The interbank settlement system operates electronically with sub-second timing. A multi-hour outage in a major settlement system would propagate to every connected counterparty. The major central banks have studied this exposure. The Bank of England published an operational resilience review in 2021, specifically referencing solar storm scenarios. The Federal Reserve has run analogous tabletop exercises. The exposure is acknowledged. The mitigations are partial. What you can do, we have spent 100 minutes on what is happening and why. The natural follow-up question is what an individual can actually do about it. The honest answer is that for the largest scenarios, the individual response is limited. But for the moderate scenarios, which are the most likely, individual preparation makes a meaningful difference. Here is a practical, evidence-based list. We are not selling anything. We are not affiliated with any preparedness brand. This is information. Do with it what you decide makes sense. First, water. The single highest impact preparation any household can make is to store enough drinking water for 72 hours. That is 4 litres per person per day for drinking, cooking, and basic hygiene. For a family of 4, that is 48 litres. Storage is cheap. Tap water in food-grade containers, kept in a cool, dark location, remains potable for 6 months. Refresh every 6 months. Done. Second, food. 72 hours of non-perishable food per person. Canned goods. Dry rice and beans if you have a way to cook them. Energy bars. Peanut butter. The selection matters less than the calorie count. 2,000 calories per person per day is the planning target. A small camp stove with 2 to 3 propane canisters extends the menu meaningfully. Third, communications. A battery-powered or hand-crank radio that can receive AM, FM, and NOAA weather band. Spare batteries. A list of important phone numbers on paper, because your contacts list is in a device that may not be operational. A printed copy of household documents in a sealed waterproof bag. Fourth, power. A 100 to 300 watt-hour portable power station, charged. A 50 to 100 watt foldable solar panel. Together they provide enough for phone charging, lighting, and small device operation for an extended outage. Cost is approximately $300 to $700 total. This is the single largest discretionary expense in the basic preparation list. It is also the most flexible, because the same equipment is useful for camping, road travel, and routine power outages. Fifth, lighting 2 to 3 LED flashlights per household member. Headlamps are particularly useful. Spare batteries. Candles are dangerous in a stressed household and should be a last resort. Sixth, medical. A 30-day supply of any prescription medication. A small first aid kit. A list of medical conditions and allergies for each household member, printed, glasses, prescriptions if applicable. Spare contact lenses if applicable. Seventh, financial. A small amount of cash in small denominations. The argument is not that paper money will be the only form of value in a disruption. The argument is that electronic payment infrastructure depends on continuous power and continuous network connectivity, and during a moderate event one or both may be intermittent. A few $100s in cash is enough to bridge a 3 to 7 day disruption for incidental purchases. Eighth, information. Know the location of your nearest emergency shelter. Know how to manually open your garage door if it is electric. Know the location of the main water shut-off valve and the main gas shut-off in your home. Know one neighbour by name. Know one out-of-region contact for your household, who can act as a relay if local communications are degraded but distant communications are intact. Ninth, vehicle. Keep your fuel tank above 1/3. During a moderate event, fuel stations may have intermittent operation. Keep a small kit in the vehicle including water, a blanket, a flashlight, and basic tools. This is sensible during any winter, regardless of solar conditions. 10th, mindset. The largest determinant of how an individual fares in any disruption is not the physical preparation, but the psychological one. People who have thought about an event in advance respond more effectively when one occurs. They are less likely to make decisions under panic. They are more likely to act in coordination with their neighbours. They are more likely to be part of the solution rather than part of the problem. Reading this list is, on its own, a form of preparation. You are doing it right now. That matters. Conclusion: we started this video with a 32-hour window, a solar flare, an earthquake, a volcanic swarm, an asteroid pass. We walk through what each of those phenomena is, what we know about them, and what the historical record tells us about their largest plausible forms. We looked at the emerging science of solar-terrestrial coupling and the careful, partial but real evidence that the components of our planetary environment are more connected than the standard model assumes. We laid out 3 scenarios in order of escalating severity, and we walked through a basic, practical, individual preparation list. The most important takeaway of this entire briefing is the one we have been quietly making in every section. The planet is not a collection of isolated systems, it is a single system. The Sun, the atmosphere, the magnetosphere, the lithosphere, the deep magma reservoirs, and the near-Earth orbital environment are all coupled. Some couplings are strong, some are weak, some are well understood, some are not. Our institutional frameworks for monitoring and forecasting have, for historical reasons, divided the system into 4 separate disciplines with 4 separate agencies. That divide made sense in the 20th century, it makes less sense now. The November 4th sequence is a small but clear demonstration of why. We are not telling you what to believe, we are showing you data. The data is publicly available. The Space Weather Prediction Center publishes its records in real time. The USGS publishes the Earthquake Catalogue. The Icelandic Met Office publishes the tremor logs. CNEOS publishes the asteroid passes. Anyone with an internet connection and 6 hours of free time can verify every number we have given you. We invite that verification. We encourage that verification. Because the only way the field of solar terrestrial coupling matures is through a generation of researchers and informed citizens who actually look at the numbers themselves and form their own assessment. The next significant solar maximum is roughly 11 years away. The next major X-class event is anywhere from days to years away. The next major earthquake is locked into the strain accumulation of every loaded fault on the planet and will release on its own schedule. The next volcanic eruption is in the magma chambers underneath every active system. The next near-Earth object is on its existing orbit, waiting to be found or waiting to arrive. We do not know the timing. We know the inventory. We know the physics. We know what to watch. Keep watching. Keep reading. Keep verifying. And keep questioning the framing you receive from any single source, including this one. That is what informed citizenship in the modern era looks like. That is what we are trying to build with this channel, one briefing at a time. If this video gave you something valuable, share it, subscribe, hit the bell, because the next briefing is already being researched. And you are going to want to be there for it. Before we move to the practical preparation list, let me add some technical depth on the grid resilience question, because it is the single largest exposure for the typical viewer in a developed country. The global power grid is not a single grid. It is approximately 20 large synchronous networks, each operating at a particular grid frequency, 50 or 60 Hz, with phase-locked generation across thousands of stations. The networks are interconnected at certain points through direct current ties, which allow controlled power transfer between asynchronous networks. The synchronous networks are large. The Eastern Interconnection in North America covers an area larger than Europe and includes approximately 60% of total US generation. A geomagnetic disturbance affects the entire synchronous network simultaneously, so a single network failure can black out an area comparable to a continent. The protection systems that prevent cascading failure during normal operations were designed for the normal operations. They were not designed for geomagnetically induced currents flowing in the transformer neutrals. When a geomagnetic storm injects DC into the system, the protection relays receive signals they were not designed to interpret. Some relays trip transformers to take them offline, which is the intended behavior for some classes of fault but counterproductive during a storm, because tripping a transformer offline removes its damping capacity from the network and increases the storm impact on the remaining transformers. The 1989 Quebec event was, in essence, a protection cascade. The transformers tripped sequentially as the storm progressed, and the network unraveled in 90 seconds. The hardening efforts since 1989 have focused on several specific upgrades. Neutral blocking devices on critical transformers can interrupt the DC flow. Series capacitor compensation on long transmission lines can block low-frequency currents. Improved protection logic can distinguish geomagnetic events from conventional faults. Most importantly, real-time monitoring of JIC at key nodes provides the operations center with situational awareness that simply did not exist in 1989. The North American grid has implemented all of these to varying degrees. Europe has implemented some. China has invested heavily. South Africa has invested at the margins. Other regions, including most of South America, the Middle East, Africa, and South and Southeast Asia, have done little. The grid resilience landscape is uneven, and the November 4th event happened to favour the regions that had invested in hardening. The next layer of resilience is the spare transformer pool. Large extra high voltage transformers are not standardized. Each unit is custom designed for a specific substation. The manufacturers, Siemens, Hitachi, Mitsubishi, TB build to order. The lead time from order placement to delivery is 12 to 18 months. The current global production capacity is approximately 200 units per year. The total installed base is approximately 30,000 units. A scenario that destroys 200 units is a 1-year backlog. A scenario that destroys 400 units is a 2-year backlog. A scenario that destroys 1,000 units is unrecoverable on any operationally useful timescale. The proposed mitigation is the Strategic Transformer Reserve, a pool of spare units pre-built to common specifications, stored regionally, and available for emergency deployment. The United States has implemented a modest version of this through the EPRI Spare Transformer Equipment Program. The European Union has begun similar efforts. The investment is small compared to the exposure. The political will is the limiting factor. The third layer of resilience is microgrid capability. A microgrid is a small electrical system that can disconnect from the main grid and operate independently for a period. Hospitals, military bases, data centers, and some communities have microgrid capability. During a major grid event, microgrid sites can preserve critical operations while the main grid is being restored. The technology has matured rapidly over the past decade. The cost of solar plus battery storage has declined to the point that microgrid investment is now economically attractive for many large commercial sites. The growth of microgrid capacity is a meaningful, ongoing reduction in the systemic exposure of modern society to long-duration grid failure. There is one more dimension of preparation that we should address explicitly, because it is the dimension most often underweighted in popular discussion. The dimension is community. In any disruption longer than 24 hours, the determinant of how a region fares is not individual stockpiles. It is the degree of functional cooperation between neighbours, between businesses and customers, between local government and citizens. A region with strong community networks recovers faster from any disruption than a region with weak networks, regardless of stockpile level. The 2011 Tohoku earthquake demonstrated this clearly. The communities that fared best in the months after the rupture were not the wealthiest. They were the ones with established systems of mutual aid, intergenerational relationships, and routine cooperation. The implication for individual preparation is that the highest value time investment after the basic supply preparation is in the cultivation of relationships. Know your neighbours by name. Know which of them has a generator. Know which of them is a nurse, a mechanic, a ham radio operator, a farmer. Know which of them might need help in a disruption. The elderly, the chronically ill, the families with young children. Offer routine help in normal times. Accept routine help in normal times. The reciprocity that emerges from these small exchanges is what scales up to functional cooperation in a crisis. No amount of canned food substitutes for knowing the person across the street. The second dimension that deserves more emphasis is information literacy. In a disruption, the most valuable signal is reliable information. Reliable information is the difference between making rational decisions and reacting to rumour. The skills of distinguishing reliable from unreliable information, checking primary sources, cross-referencing multiple agencies, recognising sensationalist framing, are the same skills that make for an informed citizen in normal times. Cultivate them. Read primary agency reports occasionally even when nothing is happening. NOAA's daily briefing. The USG's earthquake feed. The Smithsonian Global Volcanism Program weekly update. The CNEO's Close Approaches table. These are public, freely available, and consistently more useful than any news article summarising them. The cumulative effect of 6 months of reading primary sources is a step change in your ability to evaluate any future story about space weather or natural hazards. The third dimension is mental preparation for the specific reality that not every scenario is recoverable on an individual scale. The largest scenarios we walked through earlier, the catastrophic Miyake plus Carrington combined event, are not events that any individual preparation list can fully address. The honest framing is that individual preparation makes the difference in moderate events, contributes meaningfully in severe events, and is partial in catastrophic events. The recognition of that limitation is not a counsel of despair, it is a counsel of accuracy. Prepare for what is most likely, maintain awareness of what is most consequential, and recognize that the deepest form of resilience is the social structure within which you live, not the supply closet within which you live. There is also the question of which countries and regions are best positioned to absorb a major solar event and which are most exposed. The geographic distribution of risk is not uniform. The highest physical exposure to JIC induction is at high geomagnetic latitudes, broadly, the regions north of 50 degrees and south of 50 degrees. That includes most of Canada, most of Russia, Scandinavia, the northern United States, the United Kingdom, most of Argentina and Chile, southern New Zealand, and southern Australia. The lower latitude regions are not immune. The 2003 Halloween storms damaged transformers in South Africa, which is at approximately 30 degrees south, but the average exposure is lower at lower geomagnetic latitudes. The grid hardening level is partially correlated with the physical exposure, but not perfectly. The United States and Canada have invested in hardening because of the 1989 event. Northern Europe has invested less because the worst events historically have spared their grids. The United Kingdom, despite being at high geomagnetic latitude, has done limited hardening. China has invested heavily in the past 10 years. India has begun hardening efforts. Latin America has done little. Africa has done very little, with the exception of South Africa. Australia has done moderate hardening, particularly in Tasmania and Victoria. The result is that the global exposure to a major solar event is not evenly distributed, and the recovery from such an event would unfold geographically in a pattern very different from the pattern of the event itself. The financial implications of this asymmetry are worth considering. The countries with the largest grid hardening investments are also the countries with the most extensive financial market infrastructure. A scenario in which the well-prepared regions ride through an event with limited damage, while the unprepared regions suffer prolonged outages, could have major implications for global trade, capital flows, and political stability. The 2020 to 2022 pandemic provided a small-scale preview of what asymmetric global disruption looks like. A severe solar event would be a larger-scale version of the same dynamic, with the differences in regional resilience determining who experiences the event as a temporary inconvenience and who experiences it as a multi-year economic depression. There is also the question of cascading interdependencies. Modern critical infrastructure is not a set of isolated systems. Power depends on natural gas. Natural gas depends on power for compressor stations. Water depends on power for treatment and pumping. Telecommunications depend on power and on functioning satellite systems. Banking depends on telecommunications. Food distribution depends on banking, on power for refrigeration, and on fuel for trucks. The interdependencies are deep and tightly coupled. A 72-hour disruption to power in a major region causes cascading effects in every dependent system within 24 to 48 hours. A 30-day disruption causes adaptations and rerouting in most systems. A 6-month disruption causes structural reorganization. A multi-year disruption is recovery from a different state. There are 3 more practical preparation items that did not fit cleanly in the main list, but deserve mention. The first is documentation. In any extended disruption, the people who fare best are those who can prove who they are, what they own, what their medical conditions are, and where their assets are. Print copies of your insurance policies, your medical records, your property deeds, your vehicle titles, and a basic identity packet for each household member. Store them in a sealed waterproof bag. Take a second copy and give it to a trusted friend or family member in a different geographic region. The cost is approximately 4 hours of work and $30. The value, if needed, is enormous. The second is the topic of evacuation versus shelter in place. The choice depends entirely on the nature of the disruption. For a moderate solar event with a multi-day grid outage in your region, shelter in place is almost always the correct choice, provided you have the basic supplies discussed earlier. Evacuation creates exposure to road conditions, fuel availability, traffic, and the difficulty of finding shelter in an unfamiliar area. For a localized hazard, flood, fire, immediate physical threat, evacuation is the correct choice, with a pre-identified destination and route. The decision should not be made for the first time during the event. It should be discussed, planned, and rehearsed in advance with every household member. The third is the topic of vehicles. Modern vehicles, particularly those from 2010 onward, contain extensive electronic control systems. There has been speculation that a major solar event would render modern vehicles inoperable. The reality is more nuanced. The geomagnetic component of a CME does not directly damage automotive electronics. The vehicles are at ground level, shielded by the Earth's magnetic field, and the geomagnetic effects propagate primarily through long conducting structures, not through small enclosed electronic systems. Modern vehicles would generally continue to function during and after a major solar event. What might fail is the fuel station infrastructure, pumps require electrical power, and the supply chain for fuel deliveries. The practical implication is to keep your fuel tank above 1/3 and have a small reserve of fuel for any small engine equipment like a generator. The frequent worry that a solar event would directly disable cars is, to the best understanding of the relevant engineering literature, not the primary concern. The primary concern is the supporting infrastructure. Let me close this section with the observation that has emerged from every serious resilience study of the past 30 years. The single largest determinant of how a population fares in any major disruption is not the depth of individual stockpiles. It is the speed of collective decision-making in the first 48 hours. Communities that have rehearsed decision-making, that have run tabletop exercises, that have established communication protocols, that have identified leadership and decision authority in advance, respond effectively. Communities that have not done these things waste critical hours arguing about who decides what. The cost of running a community tabletop exercise is approximately 4 hours and $0. The value in a real event is measured in lives. If your local emergency management agency runs such exercises, attend one. If it does not, organize one with your neighbors. This is the highest leverage preparation activity available to the individual citizen in the modern era. Let me add one more layer to the implications discussion. The layer is psychological. The reality of low-frequency, high-consequence events is that they are difficult to take seriously precisely because they are infrequent. Humans are evolved to weight recent vivid experiences heavily and to discount events that have not occurred in the recent past. The result is that a society that has not experienced a Carrington-class event in living memory tends to underinvest in protection against one, even when the engineering analysis indicates the protection is cost-effective. This is sometimes called the normalcy bias. It applies to solar storms, to magnitude 8+ earthquakes far from active fault systems, to volcanic supereruptions, and to large asteroid impacts. The fact that none of these has occurred in the past 100 years does not mean that the probability of one occurring in the next 100 years is 0. The base rates are well established, and they are non-zero. The corrective for normalcy bias is the conscious cultivation of historical perspective. The Carrington event happened. The Tambora eruption happened. The Tunguska airburst happened. The Lisbon earthquake of 1755 happened. The 1908 Messina earthquake killed approximately 80,000 people. The 1976 Tangshan earthquake killed approximately 240,000. The 2004 Sumatra event killed approximately 230,000. The 2010 Haiti earthquake killed approximately 160,000. These events are not abstractions. They occurred within recorded human history. They will occur again. The only question is when, and what the society of the time has done to prepare. The cumulative effect of routine awareness of these historical events is a calibrated sense of risk that is neither paranoid nor complacent. That calibration is in itself a form of resilience. Let me also address directly the question of trust in institutional sources. Throughout this video we have referenced NOAA, the USCAS, the Icelandic Met Office, CNEOS, NASA, ESA, JMA, and other agencies. Some viewers will reflexively trust these sources, others will reflexively distrust them. Neither reflex is appropriate. The agencies are staffed by scientists and technicians who, on the whole, do their work professionally and with integrity. The agencies are also constrained by their institutional positions, by their funding sources, and by their policy mandates. Their public statements are sometimes more conservative than the underlying data warrants because the cost of a false alarm is high and the cost of conservatism is diffuse. The right posture toward agency sources is not blind trust and not reflexive dismissal. It is to read what they publish, cross-check it against the underlying data when possible, and form an independent assessment. That is what informed citizenship looks like in the modern era. And it is what we are trying to model with this channel, briefing by briefing. The final dimension I want to address is the question of timeline. Many viewers, hearing the kind of material we have discussed, will react with the question of how urgent any of this is. The honest answer is that the urgency varies by category. The next moderate solar event, G3 or G4, is essentially certain within the next 12 months, probably within the next 3 to 6 months given current cycle conditions. The next severe event, G5 with major regional impact, is probable within the next 3 to 5 years. The next Carrington-class event is uncertain on the decadal timescale, but probable within the next 50 to 150 years. The next Miyake-class event is uncertain on the century timescale, but probable within the next 500 to 1500 years. The next major regional earthquake along any specific fault is probable on the decadal timescale, with specific timing genuinely unpredictable. The next major volcanic eruption is similar. The next Tunguska-class atmospheric impact is probable within the next 100 to 300 years. The next Chicxulub-class impact is probable within the next several hundred thousand to several million years. These timescales do not justify panic. They do not justify dismissal either. They justify a calibrated, ongoing posture of awareness and modest preparation. The cost of routine preparation is small. The benefit, integrated over a lifetime, is substantial. That is the framework we recommend. That is the framework we try to model with our own work on this channel. We are not telling you to be afraid. We are telling you to be informed. And we are showing you in as much detail as we can why the information matters and how to interpret it. One final practical note before we close out the preparation discussion. The most underrated preparation activity for any household, in our considered opinion after reviewing dozens of post-event after-action reports, is the simple act of writing down what you would do in 5 specific scenarios. Scenario 1. A 72-hour power outage in winter. Scenario 2. A 72-hour power outage in summer. Scenario 3. A regional event in which you have 6 hours of warning to either shelter in place or evacuate. Scenario 4. A national event that disrupts financial systems for 5 days. Scenario 5. A multi-week event that disrupts food and fuel supply. Write down what you would do in each scenario. Where you would go. Who you would contact. What you would do with your pets. How you would manage your medications. What you would do with the elderly relative who depends on you. What you would do with the child who is at school when the event begins. The act of writing the answers down forces you to think through the gaps. The gaps you discover are the highest priority items to address. For most households, the gaps are predictable. They include the lack of an out-of-region contact, the absence of a printed map of the local area, the missing prescription medication backup, the unknown location of important documents, the unknown identity of the trusted neighbours. The gaps can typically be closed in 2 to 4 weekends of focused effort. The cost is small. The change in functional preparedness is large. The deeper point is that preparation is not primarily about stockpiles. It is about decision frameworks. The household that has written down its decision frameworks in advance can react quickly and rationally to an unfolding event. The household that has not must improvise under stress. The difference between those two households, observed across hundreds of historical disruption events, is the single largest determinant of how the household actually fares. This is the central insight of modern resilience theory, and it is the central practical recommendation of this video. One last operational topic that almost never gets the airtime it deserves. The question of communication during a multi-day grid disruption. Most households assume that their mobile phone will continue to function during a power outage because the phone has a battery. The assumption is partially correct. The phone itself will operate as long as the battery has charge. What is less commonly understood is that the cell tower infrastructure also depends on power. Most cell towers have backup batteries with 4 to 8 hours of capacity. Some have small generators with fuel for 48 to 72 hours. After that, the tower goes offline. The phone in your hand will still have battery, but it will have no network to connect to. The implication is that beyond the first 24 to 48 hours of a major regional event, mobile communications cannot be assumed. Landline service, in the rare locations where copper landlines still exist, may continue if the central office has backup power. Internet service via cable or fibre depends on the same backbone power infrastructure. Satellite internet, Starlink and similar, depends on power at the user terminal, but not on local infrastructure between the terminal and the satellite. For long-duration disruptions, satellite internet with a portable power source is the most robust communication option available to most households at reasonable cost. The Starlink mini terminal, paired with a 300 watt-hour power station and a 100 watt solar panel, provides functional internet access for several hours per day under sunny conditions. Indefinitely, cost approximately $1,200 total. Whether this investment makes sense for any given household depends on the household's specific risk profile and budget. A more accessible communication option is amateur radio. A basic handheld VFR radio costs approximately $30. The license to operate it in the United States is approximately $40 and requires passing a 35-question multiple-choice test. Range is typically 5 to 50 kilometers in urban terrain, up to several hundred kilometers with elevated antennas. During major disruptions throughout history, Hurricane Katrina, the 2011 Tohoku earthquake, the 2017 Caribbean hurricane season, amateur radio operators provided meaningful communication services when commercial systems were down. The amateur radio community is large, organized, and willing to support new operators. Joining a local amateur radio club is a high-leverage, low-cost form of preparation that also produces a community connection. The mention of amateur radio brings us to one final dimension that the practical preparation literature consistently underemphasizes. Skills are more durable than supplies. A pantry of canned food serves a household for 30 days at most. A skill, first aid certification, basic mechanical repair, food preservation, water purification, navigation without GPS, gardening, animal husbandry, serves indefinitely. The acquisition cost of a skill is time, typically 20 to 100 hours per skill, often free. The lifetime value, integrated over decades, vastly exceeds the value of any equivalent investment in stockpiles. The recommendation is not to skip the supplies, it is to recognize that the supplies are the floor, not the ceiling, of meaningful preparation. The ceiling is the development of practical competence in the areas your specific life is most exposed to. That ceiling is, in our considered opinion, the most underrated form of resilience available to the modern citizen. There is one more dimension of the implications discussion that I want to address before we close. The dimension is generational. Most of the major risk topics we have covered in this video share a property. They occur on timescales longer than a single human career. The next Carrington-class event may arrive next year. It may arrive in 80 years. Either way, the institutional knowledge required to respond to it must be sustained across multiple working generations. That sustainment is harder than it sounds. Power grid engineers retire. Solar physicists retire. Seismologists retire. Each retirement carries with it a partial loss of working knowledge that the next generation must rebuild from documents, training, and the slower work of mentorship. The quiet success of the past 35 years of grid hardening in North America is in significant part the result of the engineers who lived through 1989 actively training the engineers who came after them. The institutional memory of that event is now carried by a generation that is approaching retirement. The next generation, the engineers who are 25 to 40 today, will be the ones who carry the response to the next major event. Whether they have absorbed the lessons of 1989 sufficiently to act on them quickly is, in our considered view, the single most consequential institutional question in this entire domain. The same generational handoff is occurring in seismology, in volcanology, in planetary defense, and in space weather forecasting itself. The implication for any individual viewer is small but real. If you work in any of these fields, take seriously the responsibility of transferring what you know to the next cohort. If you do not work in these fields, but you know someone who does, ask them what they think about institutional knowledge transfer in their specific domain. The conversation alone is, in a small way, part of the cumulative effort that keeps the response capability intact. Civilization is a collaborative project across overlapping generations. The risks we have discussed in this video will be faced by whichever generation happens to be present when they arrive. The work of preparing that generation begins now. And a closing note before our final CTA. Throughout this video, we have referenced specific numerical data, specific historical events, and specific agency conclusions. We have tried to be careful with every number. If any specific number we have provided turns out to be an error, we will acknowledge the correction publicly in a follow-up video and pin a comment with the corrected information. That commitment is the single most important thing we can offer in a domain where accuracy matters more than narrative. The data is what it is. Our job is to report it accurately and to acknowledge it when we get something wrong. That is, in the deepest sense, what it means to be a serious channel covering serious topics. We do not always get everything right. We try to never knowingly leave an error standing,